Hello, everyone. My name is Francis, and today I'm going to talk about some surprising findings of a randomized video streaming experiment we did over the last year. This is a joint work with my colleagues at Stanford and Tsinghua University, advised by my PhD advisors Keyi Winstein and Levis. Video streaming is the bulk of internet traffic, accounting for almost 75% of all. Given its prevalence, a lot of effort has been put into this area, especially on a prevailing algorithm today called adaptive bitrate algorithm, or ABR. ABR servers divide the video into chunks, with each chunk representing 2 to 6 seconds of video. Then the servers pre-encode each chunk into a couple of compressed versions at different sizes and video qualities. The objective of ABR algorithms is to decide which version of each chunk to send so as to improve users' quality of experience, or QoE, such as higher video quality and fewer stalls. ABR remains challenging today because these goals are naturally conflicting with each other. For instance, sending larger chunks would increase video quality, but may also stall the video playback. We ran a study on ABR algorithms seeking to answer the question what it takes to learn an ABR algorithm that performs consistently well over the real internet. In the past year, we have streamed more than 38 years of video to over 63,000 users. And here are the takeaways. First, the confidence intervals on the performance of ABR algorithms are much bigger than we realized. Second, a simple buffer-based ABR control published 6 years ago performs surprisingly well. And finally, it's possible to learn an ABR algorithm to outperform existing ones, but the learning has to be in situ, meaning in place on the actual deployment environment. Let's start from the first one. In order to study statistical uncertainty, we'd like to test ABR algorithms in real life and collect a decent amount of data from real users. Therefore, we built our own video streaming platform, Puffer. It's a live TV streaming website that we opened to public in late 2018 and currently has more than 100,000 users. The website is at puffer.stanford.edu. Once you register an account with us, you can watch 6 TV channels for free. We use Puffer to carry out a randomized experiment. So each time you reload the page, you will be randomly assigned to one of the ABR schemes being tested. OK, sorry about that. OK. To recruit steady participants, we purchased the ads on Google and Reddit for keywords such as live TV and TV streaming. We were also featured in many press articles as a free TV service and as a research study at Stanford. Having 100,000 users is a lot more challenging than building a research prototype. We spent a huge amount of time in building the platform and maintaining its reliability. This diagram shows the architecture of Puffer. We receive TV signals over the air with an antenna, decode and encode video chunks into different versions on 3 machines, each with 48 cores. And we serve encoded video using ABR algorithms from another 48-core server in a data center at Stanford. The existing ABR algorithms did real experiments as well. But those experiments often run between a few network nodes and lasted only for hours or days. What we have found is measuring ABR performance on the wild internet is much harder than we realized. You may need 2 years of data per scheme to reliably measure a difference like 20%. I'll demonstrate that using the results from the experiment that compares 5 ABR algorithms. But let's forget about the individual performance of each scheme for now and focus on the statistical uncertainty first. This figure is showing algorithm performance using the data collected from Puffer on January 26, 2019. On this single day, more than 17 days of video were streamed to about 600 users. Since I'm going to present this kind of figure several times, let's take a closer look. As I said, the primary goals of ABR algorithms is to have higher video quality on the y-axis and fewer stalls on the x-axis. The video quality is measured by a standard metric SIM, higher is better. On the x-axis is reversed, so the better QoE is up and to the right. For now, let's just look at those 95% confidence intervals around each point. You can see how big those confidence intervals are and how they are overlapping with each other. As a result, most schemes are statistically indistinguishable. This tells us if you perform an experiment that only streams 17 days of video, you can't really measure any benefits reliably. Any improvements you found could be just statistical noise if you don't collect enough data or consider the confidence intervals. So we ran it longer. After a week, we collected 42 days of video. As you see, the confidence intervals became smaller, but not enough. Let's look at the scheme MPC-HM. Its mean star ratio is about 0.4%, but the confidence interval ranges from 0.1% to 0.9%, twice as large as the mean value. So we continue the experiment. After a month, about half a year of video were streamed, and now the confidence intervals became much smaller. However, we are still unable to differentiate some schemes. For instance, MPC-HM and BBA produce almost identical performance. After running it for 8 months, we ended up streaming more than 13 years of video to almost 55,000 user IPs. And finally, let's zoom in this figure. We could narrow the confidence intervals down to 20% of the mean value. But remember, this is only possible after streaming at least 2 years of video per scheme. The reason for such large uncertainty is because the internet is way more noisy and heavy-tailed than we thought. Among the 600,000 streams, only 4% of them had any stalls, meaning the other 96% never stalled. Stall events are so rare in practice, which is why you need a huge amount of data to measure them. Additionally, we have results in the paper to show the distributions of watch time and throughput are also very skewed. To conclude, our first takeaway is the confidence intervals in measuring ABR performance are a lot bigger than we realized before. Without considering them by collecting a huge amount of data, any benefits we found could be just statistical noise. We believe they deserve more considerations in the future and may affect the design space of a future video streaming algorithm. Next, I'm going to talk about another surprising finding, showing that a simple buffer-based control performed much better than expected. This algorithm, BBA, is very simple. It selects video bitrate based only on user's playback buffer. Below some buffer level, it selects the lowest bitrate. And above some level, it selects the highest one. And in between, a linear function is used to map from buffer level to bitrate. Since it was published at SIGCOMM 2014, BBA has been regarded as a research baseline and was frequently outperformed by more complex algorithms. One of them is MPC from SIGCOMM 2015, which uses a classical model predictive control as the algorithm. Sometimes we refer to it as MPC-HM to stress that it uses the harmonic mean of past throughputs to predict future throughputs. To calculate how long it would take for a client to receive a given chunk, it scales the predicted throughput linearly with the chunk size. Unfortunately, these assumptions don't always hold, as we found harmonic mean is not very good at modeling throughput evolution. And predicting throughput without considering the size of chunk to send would ignore a well-known fact, which is that the observed throughput actually varies with chunk size. due to congestion control and a varying bandwidth. Another line of work uses machine learning to tackle this problem. Pensive from SIGCOMM 2017 uses reinforcement learning to learn an end-to-end ABR control. This type of learning used in Pensive, however, requires it to be trained in network simulators. And the assumption made by the paper is that training in simulation will be generalizing to real life. But the question is, we don't know how to faithfully simulate the internet yet. So we are not sure this kind of learning is feasible or generalizable. Now let's look at the same figure again, but this time we compare BBA's performance with Pensive MPC and the conservative version of the MPC called robust MPC. Again, the better QoE is up and to the right. We can see the simple buffer-based control BBA is performing surprisingly well. None of the MPC, robust MPC, and Pensive was able to outperform BBA in both quality and stalls. This is kind of contrary to the findings in prior work and surprising to us. On the other hand, it also makes sense, because compared with BBA, MPC and Pensive make more assumptions that may not hold on real internet. This concludes our second takeaway. The simple buffer-based ABR control performed much better than expected. This suggests algorithms that make fewer assumptions perhaps are more general. Finally, I will talk about how we were able to outperform existing schemes by learning in situ. I'll focus on the high-level design only and refer you to the paper for more technical details. Like MPC-HM, our ABR algorithm, Fugu, is also based on model predictive control. But it replaces the harmonic mean throughput predictor with the transmission time predictor, TTP, which is a neural network trained to predict how long it would take for a client to receive a given chunk. TTP is not a throughput predictor. It acknowledges the fact that observed throughput varies over chunk size, and explicitly takes as input the size of chunk to send and predicts its transmission time. Additionally, TTP's input also includes the low-level TCP statistics from the kernel, such as RTT and congestion window size. This is weakly crossing layers with information flowing in one direction from transport layer to the application layer. The output of TTP is not common either. Instead of a point estimate, it outputs a probability distribution over transmission times, and we found it to be useful when maximizing the expected QoE during model predictive control. Ablation studies in our paper indicate each of these features to be necessary to Fugu's performance. TTP's design enables it to be trained in situ, meaning in place on real data from the deployment environment buffer. The training data are sampled and fed into TTP as user streams. Each user stream contains a chunk-by-chunk series, including size and actual transmission time of each chunk, and the TCP statistics on the server. We use standard supervised learning to train TTP to minimize the difference between its predictions and the actual transmission times of chunks. I want to make it clear that learning in situ does not need to convert chunk-by-chunk real data into throughput traces and replay them. It does not require any network emulators for training either. Learning in situ simply means learning in place on data from the actual deployment environment. Once again, let's come back to this figure that shows average video quality versus stall ratio. And Fugu is here. It's the only scheme that outperformed BBA in both stalls and quality. Its quality variation is also the lowest among all the schemes, but we are not showing that in this figure. Additionally, this figure seems to indicate training in simulation did not make Pensive generalize in the real world. This is probably because the internet is very complex, but Pensive simulator only considered replaying throughput traces. Even though we can add other dynamics to the simulator, such as packet loss or cross-traffic, we still don't know how to choose those values to replicate the internet. So the best we can do is to retrain Pensieve on traces collected from buffer, which is a small step toward in situ learning, but still not because, as I said, learning in situ doesn't require network simulators at all. We compared the retrained version of Pensieve with the original version, BBA, and Fugu. After streaming about 4 years of video, we found Pensieve's performance was indeed improved, but was still significantly worse than BBA and Fugu. This result echoes that the generalization issue Pensieve has may have little to do with how diverse or how representative the throughput traces are. Instead, the more fundamental issue is we don't know how to faithfully simulate the internet yet. As you'll see, our approach to get around that is learning in situ, directly on data from the deployment environment. I'd like to conclude today's presentation by summarizing the takeaways. We found the confidence intervals in video streaming are a lot bigger than we realized. You may need 2 years of video per scheme to measure 20% precision. We also found the simple buffer-based control performed surprisingly well. The reason may be that it makes fewer assumptions, making it more general. The only scheme to robustly outperform BBA was Fugu, which learns a transmission time predictor in situ on real data from the deployment environment without the need of any network simulators. It's very challenging to build and maintain a platform that enables us to collect years of video and measure statistical uncertainty. We don't want everyone to go through it. So we are opening Puffer to the research community for testing ABR algorithms, network and throughput predictors, and congestion control. Please get in touch, and we'll be happy to work with you. At the end, I'd like to thank Emily Marks, who joined the project after the paper submission and performed the final data analysis. I really appreciate your help. I'd like to thank the participants in the Puffer research study and our sponsors. Thank you very much.
Questions?
I'm Zhang Song from Princeton. This is really solid work, and I really appreciate it.
Thanks.
And my question is, can you elaborate more about how do you train your neural predictive model?
This is a very good question. I can't use the slides. OK. So of course, more technical details can be found in our paper. But roughly speaking, the transmission time predictor takes chunk by chunk real data as training data. And we simply used supervised learning to minimize its predictions and the actual transmission times, basically minimizing the cross-entropy loss. Yes.
Thank you. Let's talk more offline.
OK.
Hey, Rob Ritchie, University of Utah. Also thought this was really fascinating. One thing I was curious about is whether or not you looked at like the stationarity of the data over the long periods of time, because of course that can affect how long it can take to get good confidence intervals. So do you run any change point detection or look at stationarity in that data?
That's a good question. What do you mean by stationary of the data?
So stationarity meaning that it follows the same distribution over time, as opposed to having changing distributions due to.
Did you see any concept drift? Like?
Yeah, that's a very good question. We haven't compared how the data evolves over time, but we did have some static versions of Fugu trained on some single days. And a surprising finding of ours we mentioned in the paper is that those vintages version of Fugu still performed as well as the daily retrained version. I didn't mention that our this version of Fugu is daily retrained. That probably can answer like your question partly, that the data didn't actually change too much over time, but we are not sure if it will be in the future.
Cool, thank you.
Okay, you have time for one more quick question?
Okay. I would assume the data in buffer or the server is distributive, so you can be close to the user. So my question is, in your data, do you assume the jitter, basically? Because most of the customers streaming are in the wireless, and this is keep. So would this get into assumption when you say the simple APR?
I didn't catch the last sentence.
So was this in the assumption when you said like a simple APR, was the jitter was being taken into consideration, like frequent changes basically in the
The simple PBA algorithm?
yeah, with this jitter.
With the jitter, we're not actually sure about like jitters because we didn't separate the algorithm performance on wireless networks. So I'm not sure about that.
Oh, okay. It can be happening in even wired networks. I mean, like, it's obvious in wireless more than wired. That's why I mentioned wireless. That's.
You guys should talk about that offline.
Yeah, I can
please,
take
because-
that offline.
Yeah, thank you. Let's thank the speaker again.